Hi, and welcome back to another episode of The Hidden Quantum. As always, before we get started, get yourself something to drink, and now let's get ready to look into another company that is working in the space of quantum random number generation. This time we're looking at iQrypto, with a Q of course, and the company is using classical, more or less CMOS technology rather than using light sources, quantum light sources, to generate random numbers. That should make it much easier to fabricate those devices. They should benefit more from the classical CMOS technology, so possibly more power efficient and everything else. But we will understand more about that in today's video. So if you are interested in quantum random number generators and you want to see how CMOS technology can be used for that, then stay tuned for today's video as we are diving deeper into iQrypto. And with that, as per usual, we start on their website. So here we are, iQrypto, it says up here, pioneers in quantum. From quantum physics to information, security, computing, sensing, and then you have the quantum random number generator product and the DAC. We talk about that in a couple of minutes. Bridging quantum and reality. Quantum tech is to handle. We develop engineered building blocks to bridge the gap between quantum physics and real-world applications. And here we have the quantum random number generator, the star of the show. So by exploiting fundamental quantum noise, and I will talk about that in a second, what I understand this to be from my research, we generate statistically robust and irreproducible bit streams, so random numbers, right? Our work bridges the gap between theoretical randomness and real-world integration, addressing challenges in unbiased entropy. This enables a new standard of randomness suitable for cryptography, simulations, secure communications, and any system where unpredictability is critical. And then there's the DAC, right? This is visible here. So data acquisition system. The ITRA acquisition board is optimized for quantum systems where bandwidth, timing, accuracy, and low noise are critical. ITRA is for advanced applications, hardware in the loop setups, and real-time monitoring. With onboard visualization and flexible integration options, it supports engineers and researchers in building reliable data-driven systems from lab to field. And then where to get started, get in touch with them, a link to the latest news, I guess, and then some products linked down here. The company is registered in Belgium out of the European Union. Now, let's quickly check out the quantum random number generator chip. Let's see what they state here on the website. So I think that's more or less what we've seen already. Then there are some information here, how this has been benchmarked. So by the NIST SP890 A, B, and C cryptographic standard. That is, I think, also what others are using. Where it gets interesting is when we look at the size. So here you see the die size of 1.5 by 1.5 by 0.5 millimeters. So the die is usually referred to as the little piece of wafer that your circuitry is sitting on. So for example, if you're looking at your typical CPUs, you have much bigger die sizes. If you're looking at sensors like temperature sensors and so on, they're usually very small, similar to what we see here. There's of course a lower limit also in terms of die sizes. So if you're looking, for example, into modern smartphones, they can get very, very tiny. So even sub-millimeter range, I would say, if you're looking at that. But there's a certain limit at which you can't really pick and place them anymore automatically in your systems, and like taking the components and putting them on the printed circuit boards where they are then soldered by a so-called SMD. So there's a lower limit also of size, but 1.5 by 1.5 by 0.5 is still very well pick and placeable, but a very small die size, especially compared to the ones that are using optics technology, which we've been talking about in previous. If you haven't seen them, go check out the Hidden Quantum Champions. And then what is also important here, ultra low power consumption, so just 15 milliwatts, which makes them ideal for embedded and battery powered device. Works with USB, Ethernet, or standard communication protocols, yada yada yada. Then there are some more technical specifications here, so I guess that one is important. MRTNs per second, so million random true numbers per second. Okay. And then we have, again, what we saw before, applications for that. And then, yeah, some more information down here, embedded systems, and some questions and answers. Now, let's take a step back. And rather than going through all of that, let's quickly discuss how that actually works, because they always compare it. If you're looking at, let's say, the company communication, it's compared to an hourglass, like the cent hourglass, but for quantum. So how does that actually? If you're looking at the world of quantum physics, electrons, they are these little wave packages. So they can behave like particles, they can behave like waves. Now, if you have, for example, an isolator, an insulating material, then the electron cannot go through, right? So we call that a barrier. Whereas in a conductor, like a piece of metal, the electron can freely move around because, or at a very low friction, move around because it's conducting. Now, if you have, for example, a very, very thin isolator or just vacuum, and you put two metallic contacts very close to each other, then in classical physics, the electrons cannot move from one side to the other because they would need to basically free themselves from the material, go through the vacuum and then to the other side. So naturally, that's not happening. It starts happening if you apply, for example, a very, very high voltage. So this is what you usually do, for example, in X-ray tubes. So you have one piece of metal, you heat this up, so you give it a lot of thermal energy, so the electrons move very, very fast in there, and then you apply a strong magnetic field, and that is then enough to rip the electron out, accelerate it, and then it usually hits, for example, a tungsten target where it then produces this X-ray. Now, in this case here, what they are doing is they're using diodes, and they're using a quantum effect. So let's come back to our two metal electrodes, right? There's a quantum effect that allows electrons to go from one to the other metal, even if the barrier is technically too high, so the electron doesn't have enough energy to cross them. That one is called quantum tunneling. That has to do something with the fact that electrons behave like waves, and the wave function of the electron is basically not, let's say, stopping at the border of your metal block, but it's leaking a little bit into the vacuum. So the wave function is more or less correlated to the probability of an electron existing in a specific spot. So if you have a wave function for an electron, usually it looks like you have this very steep profile where the electron is located at one position. That's what we classically would call a particle, right? But then you still have these wings that are going off this peak, right? And now there's a very, very small probability that the electron can also be measured somewhere in there, right? And now if you have two metal blocks, it could happen that one of these electrons kind of jumps or tunnels from one block into the other one. Now you can create such a system also with a so-called diode. What are diodes? Diodes are semiconductor elements. So you find them, for example, in the device that you're using to charge your phone. You find them in your electric car, you find them in your computer. They're also part of transistors. They are junctions between P and N doped silicon or P and N doped semiconductor. So silicon is the main semiconductor material. A P doping means that you have, let's say, less electrons, and an N doping means you have more electrons. And if you put these two different regimes close to each other, you can create a barrier. Actually, a barrier where in one direction the electrons can flow and in the other directions they cannot. So that's what is interesting about a diode. You can basically create a directional, one-directional electron blocker. Basically, in one direction the current cannot flow, and in the other direction. So it helps you, for example, to rectify power that is usually AC, so alternating current. You can rectify that with a diode so that it only comes out in one direction. And if this is interesting to you as a whole topic, then you should definitely consider to study electrical engineering, because there's a lot of this stuff that electrical engineers are learning about. Now, back to the quantum physics part. Let's say you have this diode and you bias it, so you apply a voltage in the opposite direction. What happens in this diode? Well, actually, what happens is you are creating a barrier that is basically splitting your positive and your negative charge zones. And if you are applying a very high voltage, this barrier is getting very, very tiny. It's a very high barrier, but it's very, very tiny. It can be in the nanometer regime if you're using today's semiconductor technologies that are operating at very small, or that can operate at very small sizes, right? Because of Moore's law, which means that transistors are getting smaller and smaller. Now, if you do so, and if you reach a certain voltage, then it will just break down. The diode will just be killed by the whole voltage and the current will just flow across it. But if you're reaching like slightly below that, you are in this point where you have this very tiny barrier. Now, if, for example, you cool down your diode and you put it close to an ejection stream of cosmic particles or of a lot of particles, then actually a charged particle, like a cosmic particle like a muon, maybe not a muon, but other particles, they can hit in there and they can cause an avalanche. So they can actually create a breakdown of your diode. So that's what's, for example, used in so-called SIPMs. So what is it? So that's silicon photomultipliers, and they are, for example, used in the CERN particle accelerator in the very inner ring of your detector to measure specific particle traces. That's basically what I learned in my first job at university working in a lab. Or well, actually I was working first in the lab as like an internship besides my studies, and then later on I could turn that into a job for a while. So we were characterizing different diodes and the cooling techniques that were being used to actually improve the detector setup within one of the detector experiments in CERN. But now back to iQrypto. So they are biasing the diodes now, at least that's how I understand it, in this regime where you have this very, very tiny barrier so that you can actually get quantum tunneling. So every once in a while, you will have an electron that is actually tunneling, so that is moving from one side to the other side of the diode. So it creates a tiny current, and this current is completely statistical. So that's a completely quantum mechanical property, because the reason that this current is existing is only because of quantum mechanical tunneling, and that's completely probabilistic. So what does that mean? It means it's completely random. Now, in practice, it is a bit hard to measure a single electron, especially at room temperature. That has to do with the fact that there's a lot of noise, right? Your electrons are moving in the cables just because of temperature excitation. So temperature means things start to shake. They are moving around on a microscopic level. And that means you have a lot of noise just intrinsically from the ambient temperature. Now, how does iQrypto now build chips that you don't have to cool down to cryogenic temperature, because that would not be interesting anymore for IoT devices, but that can still actually rely on this quantum tunneling? Well, that's where the hourglass, right? So instead of just taking a single diode and looking at a single cent grain and using that to measure, instead of that, they're actually doing a lot of those. So they're taking a lot of those diodes and they're putting all of them in parallel, like in a big array, so that you can actually measure thousands probably of these diodes at the same time. If you're doing that, like 10,000, 100,000, I don't know, you can use semiconductor technology to squeeze a lot of those onto a very small chip. If you can measure all of them at the same time, and they are all in parallel, that means that you get enough current that you can actually measure something on a standard measurement device, like a voltmeter or a analog to digital converter, so an ADC. And what does that mean? Well, it actually means that you can measure this quantum noise, this fluctuation on your chip. So you basically measure every second what is the output signal, and that will tell you more or less how many electrons have actually been tunneling through the diode. Now, technically, that could still be something that is, for example, temperature dependent, because if you add a lot of temperature to the chip, you will have more electrons that are tunneling. Why is that? Because the electrons will have a higher energy overall, and that means maybe their wave function is smearing out a little bit more, and that means you have more tunneling. while when you're cooling them down, they're moving less, and then you will have less electrons that are moving to this barrier. So you still have this temperature dependence, and that means you are not fully random at this point yet. However, iQrypto has come up with a good trick for that, because instead of measuring just the absolute number of electrons that are going through, they're looking at, is the number of electrons odd or is it even? Or to come back to the voltage measurement, they're looking at, for example, let's say the voltage is 1 volt that they're measuring roughly, then there's some noise on that. And because of the fact that we have a quantum tunneling here, this is a Poisson noise. So it goes by the square root of the number of electrons, more or less. And that means you have some let's say, predictable noise that you have here. You can set up your measurement in such a way that you can measure this noise, and then you can just look, is the first digit, like the leading digit of my noise, is it a odd number or an even number? And that's, for example, how you would be able to create still a random number output. Let's say if it's odd, it's 0, and if it's even, it's 1, for example. And that's more or less how I understand how this setup is working. So it is using a quantum effect, and then on top of that, it is integratable into a classic chip. So that's a very, let's say, elegant way of measuring this quantum distribution. And also, as we saw before, they're measuring against this NIST standard here. So it fulfills the cryptographic. Probably there's some other magic in the algorithms happening below that, but I'm only, let's say, interested on the physics part here. And that's more or less how I understand what. This is about the quantum random number generation chip. Besides that, there is this iQrypto's, right, that we've talked about before, this data acquisition module. You see here real-time precision, 24-bit DAC across 8 analog input channels, more than 30 gigabytes per second. And I think this is then like, let's say, their measurement expertise that goes in combination with the chip, right? Because I told you before, you need to measure these voltages. And I think from how I understand it, this is basically part of the let's say, IP stack or the stack of technology that they are using, and they are also selling this as a separate piece as far as I understand. Now, as always, let's also quickly learn about the company or about the team. So we built the future, the quantum future. Here's the team. You see the founder and CEO, Alessandro Brunetti, and then you see the whole team here. So FPGA engineer, analyst. So a technical team with also some administrative assistants here. So I guess they are still, let's say, in a growth stage as a company. Here you see some partners that they are working with. We see ESA, right? There is others as well. So Silicon Eurocluster, VSL for techno entrepreneurs, and so on and so forth. And also links to social media, and so on. I think there was also somewhere something about, maybe it was on the blog, because I just wanted to quickly also point this out, right? So I'm recording this in June of 2026, and the last news here is from 2025. So this is, let's say, not completely up to date as for now. But that's about it. That's everything that I wanted to talk about in this video for today. I hope you liked it. If so, make sure to give it a thumbs up. And if you don't want to miss out on the next one, which might be likely because you watched all the way to the end, make sure to subscribe to the channel. I'm looking forward to see you in the next video. As always, stay hydrated and see you then.